Before I start my talk, if we look at the predictions of general relativity, the most remarkable ones is the black holes. The next one is gravitational waves, and maybe the third one is the singularities. Black holes, it was a mathematical object before, but now we are sure that they exist in our universe. And for a long period of time, it was thought that the gravitational waves is not possible to detect, but a few years ago, at the end, gravitational waves are also detected, so we are sure about their existence. The other outcome is the singularities, but singularities, well, we haven't seen any singularity yet. It is just a prediction of Einstein's theory of relativity, but at the same time, to understand it or to analyze it, the theory of Einstein's theory of relativity is not effective to explain the singularities. And today, I will talk about the singularities to understand them deeply, because most people think that by calculating the Kretschmann scalar, they make singularity analysis. That is not true. Understanding singularities is beyond the calculation of the Kretschmann scalar. So, I organize my talk as follows. I try to keep my introduction as informative as possible, especially for the students and for the ones who are not experts in the field. And then, in the second part, I will give this prescription of the singularity analysis. Of course, there is no common method. There is no single method. There are alternatives, because, as I will explain later on, singularities occurring at scales such that the classical general relativity is not valid at those scales, and we need a new theory. And the candidate theory is the quantum gravity theory. But at the moment, we don't have consistent such theory yet. So therefore, there are alternative methods. So my talk will be based on one of the alternative methods. And then I will close my talk with the future directions, ongoing works, and with a small closing remarks. Okay, so when we start learning general relativity, we start with this definition. To construct the geometry, of course, it is the Riemann geometry, it's a curved space-time. We define a manifold and a Lorentzian metric G, and we assume that everything is smooth functions over there. But when we solve the Einstein's equations, in most of the exact solutions indicates that there are singularities. So, what is that singularity? Singularity, by the way, according to this definition, space-time should be smooth and it does not contain any irregular points. So therefore, what is a singularity then? Singularity is a location in the fabric of space-time such that the geodesics come to an abrupt end so that it cannot continue anymore. and the deterministic nature of the theory of relativity breaks down. More than that, the laws of classical relativity becomes invalid. So there are many definitions. There is no common consensus on the definition of a singularity, but there are many of them. But most widely accepted one is the one defined by Gürtuğ in 1968. He defines the singularity as geodesic incompleteness. So this is the most widely accepted definition of singularity. Now, what are the singularities in general relativity? Well, we have cosmological singularities. The one, Big Bang, for example, Big Bang singularity is the cosmological singularity. And this is the history of our universe. If you remember Ali Gram Hoca's talk yesterday, he was saying that evolution from unknown to known. So here is the unknown. So we don't know what happened here. So classical relativity is very well up to somewhere here, but beyond that point, classical relativity fails. So we need another theory to analyze what is happening here exactly. The other type of singularity that we come across is the black hole singularities and the naked singularities. Here, what is black hole? If we consider an object with enough mass, when the star runs out its nuclear fuel, it will start to collapse because there will be no outward pressure to compensate the gravitational attraction, and then gravitational attraction will dominate the inward pressure, and then the matter will collapse. So as it collapses, there are two possibilities. We may have a black hole if we have a massive object. So when we have a black hole, we have horizons, okay? So any word line, when it crosses the horizon, the tip of cones turns into the singularity, and after a finite time, definitely the particle or whatever it is strikes to the singularity as it observed from this picture. But as I will explain later on, that there are some types of singularities that may avoid this singularity. If horizons do not form, then the singularity becomes visible to the distant observer. This time, that singularity is called a naked singularity. So this is the case in black hole problems. The other one that occurs is in the singularities in colliding gravitational waves. So we know that gravitational waves are not mathematical objects anymore. They are real. So when I was doing my PhD, my study, I was considering the interaction, nonlinear interaction of gravitational waves. And we were familiar with this picture to describe the geometry by suppressing two of the coordinates. So these regions are the plane symmetric regions. So we have singularities here, but these are not coordinates. These are not curvature singularities. But when the two waves collide, as a result of mutual focusing, a curvature singularity develops. So this singularity and the singularity in black holes spacetimes topologically are different, in fact. Although they look as a singularity, they are the name, the singularity is given. For example, in the black hole spacetimes, or in the cosmological models, the singularity is point-like. But here, the singularity develops on a surface, on a hypersurface. So it is different. So, the types of singularities, so people then try to classify the singularities. So again, the widely accepted one is the one given by Ellis and Schmidt in 1977. So the strongest singularities are the scalar curvature singularities. So as I said, this is the Kreshman scalar, and the other scalars also possible. We look at if it's diverged, we say that it is a singularity. It has the space-time is singular. So any observer definitely terminates at the singularity in their journey. And as an example to this type of singularity, we can give black hole singularities, interaction region of most colliding plane wave spacetimes, and Fridson-Robertson-Walker cosmologies, which is the Big Bang singularity. There is also non-scalar curvature singularities. So here, none of the curvature scalars are diverging, but some curves may become unbounded. So therefore, this is the case in Whymper cosmologies or singular plane waves. If we have a just plane wave, the singularities there are in this class. And also Bell-Zacharias colliding wave solution also is in this category. And the other one is the quasi-regular singularities. So we can give an example, type cosmologies, cosmic string spacetimes, and especially the fold singularities in the incoming region of colliding plane wave spacetimes are categorized as a quasi-regular singularities. So as you see, the singularities can be classified as scalar curvature, non-scalar curvature, and quasi-regular. But the picture has not been completed yet. It's not finished yet. We have to follow. Now, in order to understand the nature of these singularities, we have to draw Penrose diagrams. What is a Penrose diagram? So if you look at this, this is a Penrose diagram of a Minkowski spacetime. Flat metric, x, y, z, and dt, x, y, z extending from minus to plus infinity. So if you make a successive transformations and make the plot of the Penrose diagram, what you achieve, you describe the whole space-time within this diamond-shaped structure. And these horizontal curves describe the space-like curves, and the vertical ones are the time-like curves. And this is the past time-like point, and this is the future time-like. And these are the future space-like and the past space-like point. So the whole space is there. The diagonal lines, they just describes the rays of photons. It describes the trajectories of massless particles, but the others describes the massive particles. Now, depending on the surface that the singularity appears, it becomes, we call them space-like singularities. So if you draw the Penrose diagram for a space-like singularity, we have this structure. So if this is our universe, any world line that crosses the horizon, the tip of the cone turns into the singularity, and definitely it will fall into the singularity on this surface. And as you remember from the previous figure, the horizontal, these are the space-like curves, and since the singularity occurs on these curves, we call it space-like singularity. The other one is the time-like singularities. So the time-like singularities, for example, if we make the Penrose diagram of a Reisner-Rostrom black hole, in the Reisner-Rostrom black hole we have two horizons, if you remember, and the singularities here occurs on the vertical, which is the time-like curves. So we call them time-like singularity, but this singularity compared to the space-like one is weaker. Weaker in the sense that, look at the world lines here. A particle can cross the outer horizons and even crosses the inner horizons. So it may fall into the singularity, or we can follow another path that does not necessarily follow into the singularity. It may continue without falling into the singularity. And then, if we have time-like singularity in any space-time, it means that you can make its analytic extension. So, therefore, this can be extended analytically so that, because it is, as I said, it is not bounded. Some curves may hit to the singularity, but there is a chance to follow some other curves which may not hit into the singularity. And null singularities, well, this terminology came to our attention during 90s when the numerical relativity has developed. The people were interested in what is really happening inside black holes, because as you all know, for a Schwarzschild metric, outside the horizon is static, but inside horizon is dynamic, it's time dependent. So if you want to know something about it inside the structure, so you have to assume the metric in this form, in double null coordinates, UV, which means there is a time dependence here. It is not just as a function of R, the metric function. And this is our corresponding Einstein's tensor in the presence of electromagnetic or scalar waves. So when you write down the field equations, so these are the field equations, all as a functions of U and V, and these two are the constraint conditions. And attempting to solve these set of equations analytically, it's impossible. There is no analytic solution for that. And therefore, what the people did, they evolved numerically, and after numerical evolution, they come to this conclusion. So when they plot their Penrose diagram, they realize that when we cross the event horizon by perturbing the space-time with scalar field, for instance, the Cauchy horizon becomes first a null singularity. So the singularity occurs on the null surface, and then it turns into a space-like one. But as you see, the rest is dotted. It means that those equations have not been analyzed through the inside of the black hole. They evolve it up to a certain point, because everybody are aware that if you get close to the singularity, Einstein's theory is no more valid. You cannot apply those equations, it is incorrect. But at least they get the idea what is happening. So these are the tools for classical relativity to understand the singularities. And later on, people, they understand that if we want to understand the singularities well, we have to find another method, because classical relativity has limitations. We cannot go any further. Then, in view of classical general relativity, therefore, if you look at the literature, in 1970s, BKL conjecture was developed, or BKL singularity, Belinsky, Kalatnikov, Lifshitz. They perturbed the F. Robertson-Walker, the cosmological model spacetime, to understand the nature of the Big Bang. Okay, and there they have obtained that the universe is chaotically oscillating around a strong space-like singularity. So this was the outcome of the BKL singularity. It is completely the outcome of classical relativity. And then Poisson and Israel in 19s, they developed the numerical relativity, and when they perturbed the Reisner-Nordstrom black hole, they obtained that the curvature singularity develops, and the phenomena of mass inflation has been introduced to the literature. And then Ori and their colleagues with Burko and Brady, they studied many black hole spacetimes, especially for the charged spinning black holes. They said that the Cauchy horizon evolves into a curvature singularity with properties null and weak. So they confirmed that if a scalar field dominates the electric field, then space-like curvature singularity develops. First null singularity and then space-like. But if electric field dominates the scalar field, then first a null singularity and then a time-like singularity. So this was the outcome of the classical relativity. So then it was understood that classic understanding singularities in view of classical general relativity is limited. So we have to find another method, another theory. And the candidate theory, as I said, is the quantum gravity theory, but it is not, we don't have such theory yet. So people, they have developed some methods. So is there any common method? Actually, there is not any common method. So one of them is the loop quantum gravity and cosmology. So the leading figures in this field is Ashtekar and Bojovov, and they are students and colleagues. Here, loop quantum gravity focuses on a cosmologic singularity. So they are looking for a space-like singularities, and they are trying to understand the Big Bang singularity. And to be honest, they have progressed very well, and recently they have published an article in PRL that they consider the Schwarzschild classical extension, and they claim that they resolved the Schwarzschild singularity with loop quantum gravity theory. And as I said, their methods are based on to study space-like singularities. Another alternative method is the string theory. And here Gary Horowitz is the leading person in this theory to resolve the singularities. And some time-like singularities are resolved. The orbifold, the flop, and the conifold type geometries, they resolve the time-like singularities. And another alternative, which will constitute the main theme of this talk, is the dynamics in non-globally hyperbolic spacetime. So there are three main groups in the world that considers this method. So in this method, it is developed by Robert Wald, and initiated by Wald, but developed by Horowitz and Marov. So in this dynamics is restricted only for static spacetime. I will consider their extensions to the stationary, but there are some restrictions I will mention in the future directions. So here, what is the main idea? We say that the system is non-singular when the evolution of any state is uniquely defined for all time. So uniquely defined for all time is important here. And what is the prescription that the world proposed? They consider the scalar field propagation in a static space background. And if the space-time is not globally hyperbolic, it means that if there is a singularity in the space-time, then that surface, hypersurface sigma, is not a Cauchy surface, and the data on that Cauchy surface determine only phi in the domain of dependence. If you go outside the domain of dependence, this equation does not determine the scalar field propagation everywhere. So the main problem here is to find a prescription to define phi everywhere. So to do so, what we do, when we write down this explicitly, we separate temporal and spatial parts, okay? And the term on the right hand side is the spatial part of the Klein-Gordon equation. And what we do, we say that that spatial part is equal to minus, and we equate it to A. A is the operator here. So the operator the spatial part of the wave operator from the Klein-Gordon equation, we take it and we equate it to A, and we take its minus. And we define this operator in a Hilbert space, okay, of square integrable functions. Now, if we define this on a Hilbert space, we then formulate the problem of solving equation 8, which was this one, the Klein-Gordon equation, into the problem of finding one parameter family of vectors in Hilbert space satisfying this equation. So this is important. In most of the books, this is taken as quantum Hamiltonian constraint. And here, the derivative here actually is not a time derivative, and this equation actually is not equivalent to the Klein-Gordon equation. This is important here. And in the loop quantum gravity, if you look at the papers for loop quantum gravity, there is similar things, similar constraint, Hamiltonian constraint, quantum Hamiltonian constraint, but over there, the definition of time is different. They call it internal time, and they have some other extra structures, but the main idea is coming from this constraint. And what is important thing here, the operator, this operator is positive and symmetric operator. When you have a positive and symmetric operator, there is always extension. And the important thing here is to find a unique extension, because if there is only a single unique extension, then we say that A is essentially self-factoring. Now, what we're doing here, the well-posedness problem of initial value problem is translated into the essential self-factoringness. Now, this is the, for a free scalar particle, it takes this form, and with a solution of this one. Now, here is important. How do we define time evolution uniquely? Look, this is the operator, okay? So we are saying that this operator must be essentially self-factoring. Essential self-factoring means that it has only one extension. There is no second one. If we define initial condition, so, and if the extension is unique, then we can evolve, we can predict the wave we can make time evolution, so we can predict what will happen after a finite time. if this extension is not unique, then we should know which extension is used for evolution. And then we say that that system is quantum singular. But if the extension is unique, we say that, oh, since it is unique, by defining initial conditions, I can predict its future time evolution, and therefore that system is quantum regular. So this is the definition that we apply in our prescription for defining the, for analyzing the singularities. And definition is here. If A has only one self-adjoint extension, then A is essentially self-adjoint, and the future time evolution of a wave packet is uniquely determined by the initial data. And we say that the spacetime is quantum mechanically non-singular. If A has many self-adjoint extensions, then these equations are ambiguous and the spacetime is quantum mechanically singular. So, using this prescription, a lot of spacetime has been analyzed, but of course, here we say that you must show that the operator is self-adjoint. So how are you gonna do it? The problem is to find a way to test for essential self-adjointness. There are only two methods for doing this in functional analysis. One of them is the von Neumann criterion of deficiency indices. So in this criterion, this is the kernel that we are using. This is our operator, and this is the candidate wave function. So here we solve this, and we look to find solution which fails to be square integrable. So if you find one solution that fails to be square integrable, then we say that this operator is essentially self-adjoint. But if it belongs to the Hilbert space, then it means that it may have an extension, so it is not essentially self-adjoint. This is one of this method incorporates with this calculation. The other one is the while limit circle limit point criterion. Here, what we have to do, so we have to write the Hamiltonian operator in one-dimensional Schrödinger-like equation, and then investigate its potential. So I will not give the details. In our papers, the details are given. So we can apply these two methods, and we can define whether the operator is self-adjoint, essentially self-adjoint or not. Now, let's look at the studies, spacetime's studies so far. Of course, the first example, as I said, is coming from the Horowitz-Marov paper. They have considered negative mass Schwarzschild solution and Reisner-Nordstrom metric, and they claim that these metrics are quantum singular. So I will return back to this at the end of my talk, to the Reisner-Nordstrom case. And in their same paper, they claim also that the charged dilatonic black hole and fundamental string solutions are quantum regular, according to this conjecture. The other group that works in this field is the leading figures there is Helliwell and Konkowski. These are some of their works. They mainly consider quasi-regular singularities, Galsov, Letellier, Todt, cylindric geometries, Levi-Civita, and conformally static spacetimes. And according to their analysis, they claim that some of the spacetimes becomes quantum regular, but some of them stays quantum singular. So classical singularity is also becomes quantum singular. It means that there is something, the singularity is strong, so that it cannot yield quantum mechanically. And the other group is these guys, and some of their works, important ones, are here. They consider spherical and cylindrical topologic defects spacetime, BTZ black hole, global monopole spacetimes, cosmological spacetimes, Horovalicious cosmology, and 1 plus 1 dimensional Horovalicious gravity. And again, they also consider not just the scalar field dynamics, but they consider especially Halliwell-Konkowski in one of their paper, Maxwell fields and Dirac fields as well. So they show that in some metrics they obtain quantum regular solutions, but the characteristic property is that when the singularity is probed with scalar waves, most of them remains quantum singular. But when spin is come to calculations like the spin 1 particles, which is the electromagnetic waves, or spin half fermions, most of the singularities are healed, are smoothed out. And our group is working also in the same field. We started to our journey in 2010, and first we consider matter-coupled black hole spacetimes in 2 plus 1 dimensions. We consider both scalar field and Dirac field probe, and we claim that against the scalar field probe, spacetime is quantum singular, but fermionic probe, the singularities are removed. And in Lovelock theory also we considered together with my colleagues. And here also we confirm that the singularities are healed, because the number of dimensions is also effective here in healing the singularities. So this is the example in higher dimensions. And linear dilaton black hole spacetime is considered again in one of our paper. And as I said, here we just consider the scalar field probe, and we found that this black hole is quantum singular. Then we consider magnetically charged solutions in Einstein's power Maxwell theory, and we obtain that this is quantum singular. With my student, we consider this singularities in a model of FR theories, and we probe the singularity with Dirac fields, Maxwell fields, and scalar fields, and we show that when we probe the singularity with scalar waves, it is quantum singular, but with fermionic probe, it is quantum regular. In a global monopoly space-time, this is also a very important paper, and here we have shown that when we use fermionic waves, the space-time is quantum regular. In power law metrics also we consider, some of them are regular, some of them are singular. And in nonlinear electrodynamics in 2 plus 1 dimension is also considered. So I will not go into details. So this one also in Einstein scalar metrics in 2 plus 1 dimension. This is important. We consider this problem with Mustafa Hoca. And the first time in this analysis, we have considered the Kerr naked singularity. As you know, Kerr metric is a stationary metric, but the method is valid for static space-times. So how it happened that we have applied to this metric? Well, if you know the structure of Kerr metric very well by analyzing its inside structure, you know, in the inside structure of Kerr metric, the singularity is ring-like. So the main property is that this singularity has directional properties. It means that if you approach to the singularity arbitrarily, you don't see it. You don't feel that singularity. If you want to encounter with that singularity, you should approach to the singularity from the equatorial plane. So when you approach to the singularity with an equilateral plane, then you come across with the ring-like singularity. So when these conditions are imposed on the equations, and simplifying everything, we observe that once you write the Klein-Gordon equation in stationary metrics, there are some cancellations, and at the end you separate spatial and time part on each side of equality, and then becomes possible to apply the Horowitz-Marov criterion. And we make our analysis, and we have shown that Kerr-naked singularity is quantum regular completely. So we confirm this result also by making the analysis in retarded coordinate system. What does that mean? We transform the metric in a coordinate system so that the observer is rotating with the black hole. So that according to the observer, black hole is static. So when you write down the metric in that coordinates, you have obtained a diagonal metric, and when it is then possible to separate time and spatial part, and when you apply the methods there, we confirm that the Kerr-ring singularity is quantum regular. And then recently with my student we have considered four-dimensional Horowa-Lipschitz gravity, and in this paper we have shown that against scalar field probe, the Horowa-Lipschitz gravity, four-dimensional Horowa-Lipschitz gravity, is quantum regular completely. So we have also considered the generalization to stationary spacetime. So if you remember, this is the constraint that we have, and this has this solution, and as long as the operator is essentially self-adjoint, by defining initial conditions, you can easily predict the time evolution. So if we consider stationary spacetimes, then the Klein-Gordon equation takes this form. Here A and B are the operators, okay? So as you can see, there is no net division between time part and space part. Here space and time part comes together. So what is the general solution of this? Well, the general solution of this is this one, okay? So as long as you show B and A essentially self-adjoint, it seems that you can predict the time evolution. But it is not as cheap as that. Why? Because here we have two operators. For a unique evolution, we need this condition also to be satisfied. It must commute. But this is very expensive. So our trials has not given an answer yet. So we stopped at this point. And what is our ongoing works? The scalar field dynamics in a super extremal Reisner-Nostrom background. So here we are considering the Reisner-Nostrom with a naked singularity. It's not a black hole. Q is greater than M, so it has a naked singularity. So we consider scalar field dynamics here, but we did the calculations very, very carefully and with a detailed mathematics. And we found that, we are still writing this paper, we found that Reisner-Nostrom metric, actually it is quantum regular against scalar field probe. So this was our final, the last work that in this field, still working on. So if I come to the closing remarks of my talk, well, the applied method to static spacetimes is successful in smoothing out the classical singularities in some cases, but not all. In particular, the type of wave used in probing the singularity is crucial. So, some spacetimes are resolved, some remain singular. Why? We don't know this answer. Maybe there is something that we don't know. And we are looking to understand why it behaves like that. So maybe in the future we will be able to address this question also. Thank you very much.
My question will be really basic. I'm sorry for the beginning.
Yeah.
As far as I can understand, as a perspective, I mean, well, anyway, you take some background space-time.
Exactly.
You put some quantum field on it.
Exactly.
And I guess you calculate the back reactions on the space-time of the quantum field.
I treat the field as a test field.
As a test field. And
Exactly.
how can it, I mean, away from back reactions, how can it affect some fundamental properties of the background space-time like the singularities?
Well, we are not affecting the background space-time. We are looking for a wave test field, how it is affected from the background.
Okay.
This is our strategy.
Thank you.
Because the other question is, it goes to the other one. It is time dependent. So we don't know its exact solutions. So loop quantum gravity maybe will find way to deal with it.
Okay. Thank you.
Here, what is the main idea? When you make geodesic analysis, you do point particle probe. But here, what we do, wave particle probe. We are having wave packets, and we probe the singularity with waves, not with particles.
What's the formal definition of the extension of a self-adjoint operator?
Well, this is a mathematical formalism. Any operator that is positive and symmetric, the domain of dependence that you are looking for it, you can extend its domain to cover some other domains as well. So, if you have, in our strategy here, if we have extension of the operator, then that operator is essentially not self-adjoint if it has extension. So our crucial point here is the essential self-adjointness. And this was the question that I asked you when you are, because mathematically there may be some extensions.
Yes, but
The domain of dependence, what I'm saying, the domain of dependence.
if, for example, we have a physical system,
Okay.
Hamiltonian, like a spin system, do we have to consider extensions? Because the Hamiltonian is fixed.
The spin system, for example, we are considering Dirac particles, Dirac equations, which is fermions. It has a spin. So we apply the same strategy. We take the spatial part of that operator and we are checking with the von Neumann deficiency indices theorem or Weil limit point limit circle theorem, whether it is essentially self-adjoint or not. Otherwise, if it has extension, then our conjecture fails. I don't know if it is related to your case also, and I think it should be incorporated like that. So your arguments will be based on more concrete background.
Okay, small, please.
Oh, sorry. You mentioned about the study of the singularity using Holland-Lipschitz gravity. You can get the singularity solution.
Yeah, we picked a special solution from the Holland-Lipschitz gravity. Within that theory, there is a Kihagias-Svetsos black hole spacetime. I don't know if you know that solution. It is the fundamental solution in the Horova-Lipschitz gravity. So we analyze that metric. It's a black hole spacetime in this theory, and there is an additional quantum parameter there. So when you take that quantum parameter large enough, the space-time in the far region becomes Schwarzschild-like. But in the near region, it is not Schwarzschild-like, it is something else. So we consider over there, because it admits naked singularity, so we probe the singularity, naked singularity, within that space-time.
Okay, thank you to Professor Dr. Özay Gürtuğ.